Hello everyone, this is Shay and I'm going to present Linear to Predict, a topological stacking method for link prediction on temporal networks today. In network science, people are often interested in studying the structure of a network. However, more often than not, the real-world data are partially missing, and thus we seek to perform link prediction in order to better understand the structure of a network. For example, people's behaviors are affected by their peers, so for a social network recommendation, researchers can use static link prediction. There are many algorithms developed for prediction of static network. Gizman et al. Proposed a stacking method which utilized topological feature, embedding-based and model-based feature to produce optimal prediction on static network. However, networks are always changing with time. So to predict or recommend something in the future, we will have to perform link prediction on temporal networks using the current layers as the information we have. To this end, we seek to adapt the static stacking method to temporal networks and explore if adding temporal features will improve the prediction performance. There are different settings for link prediction. Sometimes people will allow access to the last layer to be predicted, which is usually the case with stochastic block model-based tensor methods. But our settings are different, in that we consider the last layer missing entirely. In other words, other than the number of nodes that should appear in the network, we do not have any information on the last layer. Like in this figure, we will consider the only information we saw are T0 and T1, and thus we want to seek if it is possible for us to predict T2. Also note that we do not consider each layer as an aggregation of the graph, meaning that each layer are a different time snapshot. So the edges in layer 1 will not necessarily appear again in layer 2. For example, we know everything about the network in May and June, but we're at the beginning of July, and thus we want to see if we can predict what will happen next. Two more things worth noticing. First, we are uniformly randomly sampling edges in this network. However, this may not always be true for real-world datasets, and future direction will include study of sampling methods. And second, we're using EUC scores here mainly for benchmarking purposes. Precision recall scores are recorded and will be provided in the upcoming paper if you're interested. Now, we introduce two different numbers here, K and P. More often than not, real-world networks have more than 2 snapshots, and in fact, many have hundreds and thousands of snapshots. Even if they are correlated through time, you could now use something that is outdated to do the prediction. Thus, we have K, which represents the number of layers we trace back on time for training purposes. It is also true that since we are dealing with temporal networks, we want to calculate temporal topological features for these selected K layers. Now, in order to capture the flow of information, we take P consecutive layers from these K layers and calculate both static and temporal topological features for these layers. To better explain this, let's look at this graph here. Each of these vectors represents the concatenated features from the P layers. We have a total of K of these layers per last picture that I have shown. The last P layers are used for testing purposes in order to generate the features for the last layer, which we know nothing about. Now that we have explained how the method really works, we turn to the experiments and the results. First of all, let's have a look at the datasets we have gathered for the experiments. We have tried to gather as many temporal networks datasets as possible and end up with 19 real-world temporal networks with different sizes and comes from different disciplines. Now, before we finally show what we have found, we first need to understand what is the current state of the art and what are the individual features we have included in our method. The static features are your usual network terminologies, including but not limited to degree, beginner centrality, page rank, etc. The temporal network features are limited because some of them are not defined, and others are too expensive to calculate. But here we look at common neighbor, given that it is a well-defined temporal feature with relatively easy calculation. The other two including stochastic block model method, which is heavily based on treating the whole network as a tensor instead of focusing on localized structure, usually emphasize on the community structure. Last but not least, we have the machine learning-based methods, which usually apply graph embedding methods such as GNN, GCN, along with other advanced embedding methods to generate feature and train upon. These have great performance, but usually lack the interpretability. Note that the performance of all these methods mentioned here are actually rely heavily on the structure of the data itself. We'll show you why shortly in the next few slides. First, we show the Gini importance for topological stacking features plot here. At first glance, there are a lot of information on the plot, but here there is no clear point. However, with careful observation, we found that in one of the group, cat centrality and page rank matters a lot, while in the other half of the figure, the one start to matter is the shortest path and LRA approximation score. This brings us to wonder if topological feature matters that much in this kind of different kinds of network. Will Gini importance feature as a feature vector will tell us anything about the inherent differences between these different data. With that thought, we did a simple PCA on the data with the Gini importance feature. We found that there are actually two different distinct group datasets, with only one or two datasets here not clearly grouped, like Redislow and FB Forum. This has shown us that these datasets are very different from each other. Anytime we saw a very good performance of a method on a specific dataset, we might need to wonder, is that because of the algorithm or the particular structure of that dataset? And this brings us to our next question. How will temporal features affect in this process? Like mentioned earlier, a lot of temporal features are either expensive to calculate or not well defined. We want to show if we can demonstrate stacking features actually perform the same, if not better than, the temporal feature, and thus we can avoid expensive calculation. By computing the common neighbor for static stacking and temporal and use them solely as predictors, we notice that their performance are almost the same. Well, like if the stacking method is not slightly better than the temporal feature. This proves that using stacking, we are able to capture the temporal information the temporal features are doing, and thus avoiding the expensive computation of temporal features. Also worth noticing that there are actually distinctly two groups of data, which is shown in the previous slides, which also shows up here. If you look closely, the ant network and Redislow are depending on the common neighbor features, while the other networks hardly depend on the common neighbor as a feature. This also supports our discovery that the different features could vastly affect the results and performance on different types of networks. With that in mind, we look at the performance of our method if we incorporate other different methods. Here, we basically include ML-SBM method, which is a tensor-focused SBM link prediction for temporal networks method. We also include ELSTMD, which is a machine learning-based method used for temporal networks. We incorporate their output as our own input and conduct the link prediction on the real-world networks. Here, top-down stacking means if we only use topological stacking method alone to do the prediction. Top-down stacking with ML-SBM means using ML-SBM method output as one of the features in addition to the topological stacking method. Same for the top-down stacking with ELSTMD. The top-down stacking with both is simply put both methods' output as feature for our method. The two methods' own performance by themselves are also shown on the figure. With the AUC scores for 19 different datasets, it is easy to observe that by combining all of the three methods, we are able to achieve a fairly good performance for all of the datasets, thus proving that the stacking method was able to learn to know which features is important in the prediction, and thus stacking method is able to incorporate other methods to make it work better with the topological feature stacked. Now to sum up. In conclusion, we have designed a stacking method to capture the temporal flow for link prediction on temporal networks. We proved this method is able to improve the performance of stacking and other advanced machine learning SBM methods and demonstrated the results on 19 real-world networks. We have also shown that the different structure of networks could lead to different importance in feature importance, and thus inherently different prediction methods should be tested on all different structured datasets. What's more, we compare the stacking static features and the temporal features. By doing that, we have shown stacking features are as good, if not better than temporal features, which save us some computational expensive tasks of computing those features in link prediction in the future. Thank you for listening. I will sum up now, and the paper is in preparation for final submission, and it will show up on arXiv very soon. I hope you like my talk, and I would like to thank my colleagues for their helpful conversation. I'm very glad to take any question now.